Welcome to this edition of the NITheCS Colloquium. This afternoon, we have the big pleasure of having Professor Amare Abebe with us, who was very happy to be able to complain in person about all the emails I haven't replied to. So, and I explained to him the procedure. Just send it again. Yeah. So Amare is originally from Ethiopia. He studied at Addis Ababa, his BSc, and completed his postgraduate studies at UCT. But now he's professor of cosmology at Northwest University in the Center for Space Research there. Since 1 week, he's the president of the African Astronomical Society. So congratulations, well done for that. And, and today he will speak about all the things we don't know about the universe, yeah, which is roughly 95% or even more. Yeah. So Amara, thank you very much for coming all the way from Potchefstroom. We are very much looking forward to your talk. Thank you.
Right. Thank you so much, Francesco, for introducing me and also for giving me the opportunity to talk about the dark stuff. About the there's an echo. There's an echo here. Should I probably? Okay. Yeah. Yeah. So let's start with the cosmic drama, and I'll take you through the um, the full story as much as possible of the dark stuff. So what you see here is a chat GPT generated um, cosmic wave simulation. It's basically the distribution of the large scale structure in the universe, galaxies, clusters of galaxies, and filaments and voids and everything there. So that's what we refer to as the universe being the stage. And these things here are merely the players. So we talk about gravity and what it does to the cosmic wave and what kind of incompleteness we have about our understanding of gravity that led to this talk of the dark stuff, and whether there are any other things that are also worth considering or not. So the outline of my talk, I'll briefly talk about the foundations of gravity, the dark side of the universe, namely dark matter and dark energy, and what we recently have discovered as the cosmological tensions, what they are and what are the implications and how we solve them and things like that. And then I'll briefly, very briefly, talk about my own research in terms of addressing some of these issues of gravity and tensions. Okay, and then of course I will give summary and outlook. All right, so let's talk about gravity. So there are four fundamental forces in nature. We have the so-called strong interaction and weak interaction that only act effectively in the subatomic scales. And then we have the electromagnetic interaction, which is ubiquitous, and it acts on large scales as well. But then we have also gravity as one of the four. And if you look at the relative strengths of the four forces, you'll see that gravity is much, 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 much smaller, weaker than, for example, that of the strong interaction. Whereas the strong and the weak interactions work on very short scales, subatomic scales, and the electromagnetic interaction works on large scales as well. But because the electromagnetic interaction only effectively works if we have a net electromagnetic charge, for example, and the universe is electromagnetically neutral, the effect of electromagnetic forces is negligible on the dynamics of the universe. So that leaves gravity as the weakest but the most important force in controlling the fate of the universe. But what exactly is gravity? And the answer to that depends on who you asked. If you were living in ancient Athenian society and you were wondering about the nature of gravity, Aristotle would have you think that it is simply the tendency of objects to move back to their natural abode, which is the Earth. So things would fall toward the Earth because that's where they have to be, that's their natural place. Um, but then, of course, these were purely philosophical ponderings without any mathematical or scientific foundation at the time. And then someone in the 7th century by the name of Brahmagupta that I managed to find in the literature uh, recognized gravity as an attractive force. And then, of course, you have Isaac Newton in the 17th century who formulated the mathematical foundations of gravity as that fictitious attractive force that exists by the mere existence of massive bodies in the universe. And fast forward to the 20th century, Einstein comes and tells, oh, there's no such thing as gravity. Actually, things fall toward the center of the curvature created by their existence or by the existence of other massive bodies in the space-time. So gravity is the manifestation of the presence of matter in a space-time that it creates. So you see, for example, some of the artistic impressions of what space-time curvature would do. If you have a flat space-time, light would travel on a straight line on that flat sheet. But if there is a massive body there and creates curvature, even light would bend around that curvature. So when Einstein developed the general theory of relativity as the theory of the curvature of space-time and how things would be forced to move around that curvature, um, he formulated this set of equations. These are 10 coupled partial differential equations for some of you who would recognize those in the mathematical disciplines. So this term here describes the geometry of space-time. That term there describes the presence of matter in that space-time. So there is some kind of proportional relationship between the curvature and the mass that produces it, or the matter that produces it. So there is a long story around that, but when Einstein tried to solve some of the implications of these field equations, he realized that the universe expands. So it's not static, it expands or contracts. So he didn't like that idea because we're talking about the early 20th century and the general understanding was that the universe was static. There was no expansion or contraction in the space-time, in space. So he added this extra term here that will play a very prominent role in our discussions of the dark energy story there. So he added that term so that the universe would remain static. And when observations eventually showed in the late 1920s that the universe is actually expanding by virtue of astronomical observations, then he abandoned that term here. And you might have read that he referred to it as one of his biggest scientific blunder, basically. But turns out that a few decades later, that term would come back to haunt us as dark energy, because in the late 1990s, people discovered that the universe is actually not only expanding, but speeding up in its expansion. And the general understanding was that until that time, the universe was expanding, was understood to be expanding, but at a slower and slower rate, because there is matter in the space-time that under the pull of gravitational effects, it will eventually contract. That was the understanding. So when this accelerated expansion was discovered, scientists did not have any explanation for that, so they thought maybe bringing back that term there but this time not to stop the expansion, but to somehow accelerate the expansion might help. And that's where the story of this dark energy begins. So when we talk about the expansion of space-time, some of you might wonder what that means. So if you have two galaxies there, at some point in time, you measure the distance there, and you measure their distance at some other later time, you see that the distance between these two galaxies has increased. And this happens to almost all the galaxies in the universe, not just to particular galaxies, but to all the or most of the galaxies in the universe, because there are some special exceptions, like our galaxy and the Andromeda galaxy, for example, have their own local effects that make them come closer to each other rather than move away from each other. So when that happens, the only explanation one can come up is to say that the universe must be expanding. And that's how this whole idea of the expansion of space came about. So because of gravity, we can explain a number of cosmological phenomena, such as, for example, the bending of light that I tried to show at the beginning. There is this other issue of gravitational waves that has been making the news in the last few years. For example, Einstein had conjectured that if general relativity, the true theory of space-time, there must be some kind of waves that would be ripples of space-time uh, um, um, because of the acceleration of massive bodies in that space-time. And 100 years later, almost to the year, gravitational waves were discovered, and so many other things like the Big Bang itself. You can only explain it through the effects of gravity. The cosmic microwave background that was some kind of radiation that was emitted about a few hundred years after the Big Bang, which plays very significant roles in our understanding of the structure of the universe today and so forth. How the first few elements, just moments after the Big Bang formed, the dynamics of galaxies and satellite galaxies around them and things like that. How large scale structures in the universe, and by large scale, I mean scales bigger than galaxies form. And of course, the expansion of space itself, you can only explain it through the understanding of gravity. These equations here is just to show you how the expansion of the universe is expressed in terms of what we call the Hubble parameter there, which I will mention when I talk about the tensions later. And that expansion is controlled by the presence of matter in the space-time, the geometry of the universe characterized by the quantity k there, and this extra term, the lambda term that was removed from the field equations at some point, but is now brought back as a dark energy component. And this equation here tells us how that expansion changes, the rate of that expansion changes over time. So it's an acceleration kind of equation there. And you'll see that if we have normal forms of matter in the space-time, these two terms here, rho and p, this is energy density and pressure terms, should be positive for normal kind of matter. And you cannot explain the acceleration of this universe if you have only normal forms of matter. So the only way you can get a positive term on that side is if you have this extra term dominating over the other negative terms, because there's a negative term there. And that's how you would explain that you cannot explain the accelerated expansion of the universe today without the need for something extra in the form of a dark energy. And the placeholder for dark energy at the moment is that cosmological constant. This is the most dominant and consensus term for dark energy at the moment, but as I will show briefly in the coming slides, that's not the only game in town. Okay, so Einstein described gravity as the curvature of space-time, but now there are three ways of understanding that curvature. And the most prominent one is, of course, the one of the that follows the Riemannian geometry, where your curvature is described by the uh, rotation of a vector transported along a closed curve doesn't come back to its original position. If you rotate this vector there, it doesn't come back to its original position. There is that extra deviation from the original position, and that you can only describe that in a curved space-time. If the universe or geometry in general is flat, purely Euclidean, that vector transport along the curve would have come back to that original direction. So this is how you describe the curvature. And this extra terms I wrote down there is just to show that in that geometry, we assume this quantity here, which we call the affine connection. It's symmetric in the lower indices, and the metric that describes it is also symmetric in those indices. I'm mentioning that because there will be one case where that will not be true. So the other case, the other manifestation of geometry, um, uh, gravity is the form of torsion, where you have two vectors, you parallel transport them, make a closed parallelogram in usual Euclidean geometry. That's how we learned vector addition, for example. That's because we assume they form a closed parallelogram. If that does not happen in a certain geometry, we say that that geometry has torsion. And that's how we describe a torsion-based gravity in that sense. And the other one is we usually assume that if we parallel transport a vector, it maintains its direction and its length is preserved. And in certain cases where that does not happen, we say there is a non-metricity. So it only applies, that preservation applies if the metric is symmetric, and if it's not symmetric, the divergence of that answer will be non-zero, and that's the result we say it's a non-metric uh, geometry. And in that sense, when you parallel transport the vector, sometimes can get longer, sometimes can get shorter, and so forth. There is a whole generalization of gravity based on that. So this is general relativity based on that first curvature description. This is the teleparallel equivalent of general relativity that's based on torsion. And there is this other formulation of gravity based on the non-metricity formulation of gravity, yes, that I mentioned. And when you generalize general relativities that I will mention later, you just change the action, for example, by some general function of the Ricci scalar there. You get an f of r theory, which I will briefly mention because that's one of the things that I've been working on. And when you generalize the torsion scalar there in the action by a general function of the torsion scalar, you'll get an f of t theory, which I will also mention. And if you have the scalar, the non-metric scalar generalized to a generic functional, it becomes an f of q theory of gravity. So now let's talk about the dark side. So based on general relativity, our current cosmological paradigm is that of a four-dimensional maximally symmetric space-time that started off at the Big Bang about 13.8 billion years ago and has been expanding ever since. We assume that on the very large scale, not on the scale of the solar system, for example, or the galaxy, but on clusters of galaxies and above, if you look at the universe, it looks more or less the same in all directions. If you look in all directions, or if you look at all locations. So that describes what we mean by homogeneous and anisotropic universe. No preferred directions, no preferred locations in the universe. But that's only true on very large scales. If you zoom into very small scales, this is, for example, the picture of the universe that uh, uh, one could see about 380,000 years after the Big Bang, you'll see certain fluctuations that are of the order of 1 in 10,000. This is 10,000, 100,000. But if you look at things on very large scales, it looks more or less the same. And then the other assumption we make, and one of the things that I will mention how we can relax that, is to assume that the distribution of matter in the universe follows a perfect fluid assumption. And I will mention what that perfect fluid means later when we try to relax it to explain certain things. So what are the challenges of this cosmological paradigm? Well, the isotropy and anisotropy assumptions are very simplistic. If we look at the universe on smaller scales, and that might have other effects like back reaction effects, then the universe is not exactly homogeneous and isotropic. So there must be some kind of effect that one loses when we make these big generalizations of a universe being isotropic and homogeneous. And then we also have the accelerated expansion that I mentioned. This acceleration happened at about 5 to 6 billion years ago, rather, 5, 6 billion years ago, meaning that around 9 billion years ago, the universe started accelerated. So at around this redshift, if you look at those in terms of redshift. We do not know what exactly this cause of the accelerated expansion is, but the usual thing to say is that there must be some kind of dark energy that, and it's a form of energy that makes galaxies move faster away from each other, but we do not know it, but it's a form of energy, so let's call it dark energy. We don't know it. And that has a precursor in the dark denomination, because decades back, there was this discovery that the amount of matter that we have in the universe doesn't explain some of the things that happen in the universe, like the rotation curves of galaxies. If you have this some satellite galaxies or stars moving around the center of a host galaxy, the velocity was supposed to decrease as you move away from the center, according to this projection. But it turns out that the velocity actually has this kind of shape. And the only explanation one could come was to say that there must be some kind of missing mass that we cannot see, exists in the form of a non-electromagnetic presence. It cannot emit light, otherwise we would have seen it, but it has only gravitational effects. So they call it dark matter. So that was before dark energy. It's a form of matter. It has gravitational effects. It clamps things, brings things together, whereas dark energy makes things fly away from each other. So based on this, it has been concluded that around 95% of the matter energy content of the universe exists in the dark sector. That is around 68% of that in the form of dark energy, and about 27% of that in the form of dark matter. So all the stuff that we can see in the electromagnetic spectrum, people, planets, stars, galaxies, all those trillions of galaxies out there, they only make up 5% of the total energy and matter content of the universe. So the remaining 95% is unknown and exists in the dark sector. And then there are some problems to this, of course. One is that we do not know what the nature of dark energy and dark matter are. So it's everybody's game. So for example, if you want to model some kind of physical property of dark energy, dark matter, that does not contradict existing theory, of course, then you're not going to be criticized, because we don't know about the actual nature of dark energy and dark matter, except that we know they have certain effects, physical effects that can be measured. And if you assume, for example, that the cosmological constant term that I mentioned earlier is the actual candidate for dark energy, then we also run into some problems. Because that term that Einstein introduced, if you measure it from two predictions, one from quantum field theory and another one from cosmology, then the two values that you measure are about 120 orders of magnitude apart. And that is the biggest discrepancy one can make in any scientific prediction that has ever been made in any scientific prediction so far. So that makes the cosmological constant as a candidate for dark energy very unattractive. And then the other thing is this so-called coincidence problem. You notice that the present components, the present day components of dark energy and dark matter, the 68% and 27% that I mentioned, if you take the ratio of the two, it's more or less one. It's an order of magnitude of one. But if you look back in the past, like billions of years ago, dark matter used to dominate and dark energy was minimal. So the ratio between the two is extremely high in favor of dark matter. If you now take the same ratio into the far future, dark matter will be negligible and dark energy will be dominant. So if you take the ratio of the two, dark energy would be much higher than dark matter. So an extremely large ratio, of course. So how come this ratio is of the order of magnitude of 1 today? How come the dark energy and dark matter components are of more or less the same magnitude today? This is referred to as a cosmological constant coincidence problem. Um, you can call it a very anthropic argument to think that we are somehow special. We live in a very special moment where dark energy and dark matter exist, but the curiosity still exists. How is this possible? So there must be some kind of fine tuning that exists to do this. And then, of course, the other thing is there are way too many models of dark energy and dark matter that are in the literature because we do not know the actual natures of dark matter and dark energy. So anybody can just come up with a model and say, this is my model that fits the data, so this is your dark energy, or this is your dark matter. So that's problematic. And then there are also some problems that are supposedly solved by cosmological inflation. These are early universe problems. There is something about the horizon problem. For example, how come vastly separate regions of space share similar properties today, whereas they never had the chance to communicate? Because, for example, if you look at two portions of the CMB that are 46 light years apart, and they share similar properties, you might wonder how did they share this kind of similar 46 billion light years apart, whereas the actual radius, according to, for example, projections from the expansion of the universe, if something drastic did not happen in the early universe, should have been in causally discommunicated region. So how did this kind of sharing of similar properties happen? That's referred to as the horizon problem. How come the universe is so flat today? It's another thing. How did large-scale structures form if the universe was flat, smooth, and homogeneous and all that? And then you might have heard about the absence of magnetic monopoles. There are no magnetic monopoles. We have positive charges, negative charges, but we cannot have North Pole alone and South Pole alone for a magnet, for example. Why are there no magnetic monopoles? So there are so many unknowns about this, but the current paradigm is that an extremely fast expansion phase happened just fractions of seconds after the Big Bang that uh, solved these issues. There are certain mechanisms that explain that, but there is that aspect as well. But the problem there is also that there are lots of models of inflation, more than 100 models of inflation you can find in the literature. And when something like this happens, you see that there is some problem. Okay, so let's now question the status of general relativity or our understanding of gravity then. I mean, I mentioned earlier that Aristotle had his ideas about gravity, Newton had his ideas, and then problems emerged and we had to generalize it to general relativity. So is there any reason why we think GR cannot be incomplete? There is no reason. So when there are so many problems that cannot be explained by the existing theory, the standard procedure is to look for other theories or generalizations of the existing theory that can explain this. And this is exactly what's happening here. And people have been trying to assume that either the current theory is wrong and therefore it has to be modified, or the theory is correct, but maybe we're missing some matter forms in the universe that needed to be added. So in that sense, you have this theories of gravity that introduce extra fields. You have the theories of gravity that introduce higher dimensions than the four-dimensional spacetime that I mentioned. Or there are theories that change the nature of gravity by introducing um, other things like the f of r theory or f of q theory or f of t theory that I mentioned earlier. So when you modify gravity, you can either extend the existing theory. That's, for example, what happens to the f of r gravity theory. You just make the action a certain functional of the existing GR theory. In that case, you have all these models. And then you can alter the theory itself by saying, okay, this is not a Riemannian thing, this is not a curvature thing. Instead, gravity should be described as torsion or non-metricity. When you do that, you're providing an alternative theory rather than extending the existing one that I showed earlier. So you have quite a big bunch of theories out there that try to generalize gravity. So usually what happens is that when you modify the theory of gravity, you either introduce terms on the right-hand side, in which case you are basically adding extra matter stuff, or you're introducing some extra curvature stuff on the left-hand side. So for a mathematician, this might be trivial, but it has deeper physical meaning in some sense. It's not the same to say, but you can bring this extra stuff to the left, and that's it. It brings inconsistencies from a foundational point of view. So why is this useful? Well, it brings more degrees of freedom to the system of equations. I'll briefly show you, for example, what it does when you modify your general relativity to an f of r kind of theory. And f of r is one of the simplest modifications you can make. When you do that, all these new terms emerge somehow. In general relativity, all these terms would have been zero. So by introducing these extra terms to the field equations, there's so much stuff that you can do by the extras that you get. But then, of course, it's not just a trivial matter of adding things. You should, the theory becomes more complicated. It becomes extremely difficult to solve and so forth. So we have to restrict these models based on either theoretical pathological analysis or observationally constraining them using actual data, astrophysical data, cosmological data, and that kind of thing. So yeah, this was just to demonstrate that there are some things that come out when you add extra uh, things to your field equations. And then, when we thought that adding dark energy and dark matter would solve the problem, we ran into another problem. So people somehow accepted that there is something called dark energy, whatever it is, be it a modification of gravity or an extra matter field introduced to the system. And then there's dark energy and dark matter rather, and then we're sorted. All we have to do now is understand dark matter and dark energy. We thought so. And I think about 10 years ago or less now, people start to measure things that do not make sense, even when you assume dark energy and dark matter as true facts of the scientific theory. So what are those weird things? So if you measure the rate at which the universe is expanding today, using different techniques, one of them use some early universe physics that would have predicted what the value of that parameter h naught should be today. And then another one using late time measurements like supernovae and Cepheid variables and stuff like that. Then you consistently get values that are about 5 sigma different from each other. So using early universe physics like Planck satellite that assumes the lambda CDM model when you measure the CMB, then you get a value that's around 67 kilometers per second per megaparsec for the Hubble constant today. And when you estimate the same quantity using these other late time measurements, you consistently get something around 73 kilometers per second per megaparsec. And this has happened for many observations, many uh, measurements. So you rule out this being a systematic issue, and there must be something that we do not understand in the current, either in the current data or in the current theories that produce this kind of tension. So this is one of the most prominent forms of tension called the Hubble constant tension, right? And then the other one is the amount of structure that you would expect in the universe when you measure using independent sets. You also get different values. One of them consistently predicts lower values of the matter amplitude in the universe, and the other method consistently predicts higher values. And this is called, refers to as the sigma 8 tension. So this has something to do with structure formation. The first one has something to do with the expansion history. These are two of the most prominent tensions in cosmology, but there are also other lesser known tensions. For example, according to uh, the lambda CDM cosmological model that assumes the dark energy as uh, lambda, the Einstein cosmological constant, and cold dark matter as the form of matter that dominates the universe, then universe is flat. But observations have shown that it's actually not exactly flat. There is some kind of deviation from flatness, and that is a, a, some kind of tension from curvature. And then other challenges include things like anisotropic anomalies in the CMB and some hints of dynamical dark energy that people are recently talking about that are also producing some tension in in our current understanding of the universe. So this is just some schematic representation of what I have been telling you, nothing too specific about this. This is based on this white paper that came out 3 days ago on the third, three of, yeah, on the 3rd of April, part of this so-called Cosmoverse network that I am associated with. You will see that there is a band of measurements that predict around 67 and another band of measurements that consistently, stubbornly measure something around 73 kilometers per second per megaparsec for H naught. And a whole bunch of proposals that people have thrown out to explain, and you'll see that none of them have consistently managed to resolve this issue at this point. As the same, you'll see the same here for the S8 tension that I mentioned. Some of them predict something around 77, 75. The other value consistently measures around 83. And there have been proposals to solve that, and none of them have so far consistently managed to solve that issue, to resolve that issue, to remove the tension. So yeah, this is just part of a 500 plus collaboration that I just mentioned, the Cosmoverse uh, network published as a white paper recently. And some of the possible explanations you'll see, if you are interested, you can find a whole lot of explanations, possible explanations there, suggest that we need to look for systematic errors that we haven't picked up yet. Others suggest there must be some kind of new physics beyond the lambda CDM concordance model. And yet others suggest that there must be some kind of modified gravity, or there must be some kind of interaction between the dark components that might resolve some of these issues. So these are some of the things people are looking at the moment. So yeah, I'm not going to go through all this because I just mentioned briefly what these possible modifications are or can be, but you know the jury is still out. Nobody knows why these things happen. Yeah, these are just some extensions. Well, something that I may not have necessarily mentioned is that people also talk about maybe our fundamental understanding of the nature of gravity itself is wrong. And some quantum gravity phenomenology might explain this issue. So at the moment, we do not have a quantized scheme of gravity yet. So we do not have a quantum description of gravity. In other words, it's still purely classical at the moment. The other options are maybe some of the fundamental constants, or if not all, are changing over time. They are not constants after all. The cosmological constant may not be a constant, or the speed of light may not be a constant, or the gravitational constant may not actually be a constant, or all of this may not be constants. So there is also that investigation going on. But as I said, with 95% of things unknown, everything is still under question. So these are some of the things, roadmaps, if you will, of all the potential directions people can take to look at, these tensions and solve some of the things. The problem is sometimes you think, oh, I have solved the Hubble tension, and then you go use the same theory to predict the S8 parameter, and then you see that you have made the S8 tension even worse. So it's a balancing game. Sometimes you solve the S8 tension, and then you make the Hubble tension worse. So there's this kind of degeneracy as well that people have not fully managed to resolve. So the way forward for this is basically to make a rigorous assessment of the potential systematics that I mentioned are possible things that can explain this. But many people are convinced that this is not a systematic issue. And then, of course, novel data analysis techniques might resolve this issue. Well-motivated models that should solve both. You cannot say, oh, I have solved one tension, and you realize that you have made other worse. That's not the way science works. It has to, if you have one theory, it has to explain everything, and not a piecemeal resolution of things throughout. All right, and then understanding and resolving these tensions, of course, needs uh, uh, more collaborations. It cannot be one person or a few people's work. Nowadays, science has become multidisciplinary, and that kind of multidisciplinary approach should be the way to go. And understanding and resolving these tensions might actually lead to new insights into the fundamental physics that governs the universe. So it's very important that we should not leave these things as just academic exercise. So just to briefly mention to you what I have done recently in terms of those modifications and alternative models. On the F of R side, we try to look at the matter power spectra of the universe using some kind of power law model, a very simplistic toy model, and we realize that compared to the lambda CDM model, there are certain features that one can see, and the point here is not to talk about the actual results or details of this, but to show that you can predict some features that may or may not be ruled out by observations. That's the whole point. That's the only takeaway message that you can take here, that the lambda CDM model does not necessarily provide. Here we try to use actual data, supernovae data, in this case, to just test the viability of some models. And when using that model, we can actually compare how these models fare against lambda CDM. And we can see that, for example, in this case, this model here fared better than the lambda CDM cosmological model in terms of predicting some of the things. Here, some F of the gravity theory that also we use to compare the current matter amplitude by studying the large-scale structure formation in this theory. And here, for the F of Q gravity theory, we try to use actual structure growth data to compare that with the lambda CDM predictions. And if you get some better results in the modified theory than the lambda CDM, then that can mean that this model is somehow viable in that particular aspect. and so forth. And the same here, we try to introduce, remember that perfect fluid assumption that I said is simplistic. You can also include some things like, oh, what if the fluid form is actually viscous? What if matter on large scales is viscous, or on the early universe is viscous? Does it affect the way structures form in the universe? Can we predict that now? And can we compare it against observations? And this is also some of the things we did there. And you see this table just to tell you that you can calculate all the parameters that the model has and compare them against the data and actually estimate what the best fit parameters for that model look like. Um, and then if you introduce interactions, also deviating from the perfect fluid assumption, you can predict certain things that um, might be tested against observation. One of some of the things we saw, for example, here, you see that everywhere we try to resolve the Hubble tension, we made the sigma A tension worse and so forth. So, and then you can also predict what the age of the universe is and what the matter, dark energy, um, equality looks like, and so forth. So if these things can be correctly predicted using actual data, then you can use these models to see if these are the ones that explain or whether the lambda CM does better. And then in terms of summary and outlook, finally. So the universe that we talked about has about 100 billion galaxies, and each of these galaxies has about 100 billion stars. And that's only the observable. Okay, if you look at this, this is our observable universe. And this is the part of the universe that is still um, uh, unobservable. And how do you explain things in the observable universe when you have 95% of things unknown? And then you have also an unobservable portion of the universe out there. So in terms of these ponderings, I mentioned philosophical ponderings from ancient times, for example, and then I'm coming back to the philosophical ponderings again. So we follow the scientific principle to explain phenomena. And the way it works is that you have a hypothesis, and that hypothesis should assume what we call the least possible assumptions, parsimony of uh, nature, or Occam's razor. The simplest possible explanation is the best one. Okay, and then there must be uh, a cause or a reason for everything. That's basically what the scientific method is based on. And then when you have one theory proposed, one alternative theory or modified gravity theory, for example, it should not contradict existing theory. So, for example, if you have a modified gravity that explains large-scale structure formation and acceleration of the universe, but it contradicts solar system physics that we know of, then that's the problem. So, your science should introduce what we call this non-contradiction or consilience of things. And then your theory must be falsifiable. If you propose something, then I should be able to use data to test your predictions, and then that model should be falsifiable in some sense. But then reality exists independent of our observations, and isn't science a fallible and evolving attempt to resolve it? So this is a critical question that we should all answer or ponder about. And one philosophical concept I recently stumbled upon is called critical realism, which is a philosophical framework that distinguishes the things that we know and reality. Okay, so reality is not equal to our knowledge of that reality, and cosmology, as I try to tell you, operates under incomplete data. And we have those unobservables, dark energy, dark matter, and then they cannot be directly observed, but they are inferred from the observational their gravitational effects, and this may be real causal entities, but our models are imperfect generalizations or representations. And then the cosmological tensions signal some kind of limits of our current cosmological paradigm, and it also shows the fallibility of our scientific methods that we have at the moment. So I will leave you with this, that the takeaway, in terms of future outlook, the dark sector um, might actually be richer than assumed. So we need to do more work, deeper theoretical insights and observational constraints are required to be able to resolve these issues once and for all. Okay, I thank you so much. This is just to advertise that if you want to know more about gravity, the Northwest University is organizing a conference of the South African Gravity Society in November. Join us there, and we'll tell you more about the dark stuff. Thank you.
Yeah, thank you very much, Amare, for a fantastic talk. Are there questions for our speaker? I'm sure there are. Here in Donovan, please.
Hi, thank
Hi.
you for the very nice talk. In many pictures you showed us, you had a spherical model of the universe. Is there any research suggesting a better model rather than an open surface? If you go straight in one direction, will you eventually come back to starting point or not?
That's for visualization effects, really, because the universe is, as I told you, it's a four-dimensional continuum. So to think of it as a sphere will only tell us about the spatial component of the universe. So that's just for visual effects, really, not that we think or we know that the universe is spherical in this geometry. But there are three possible geometries that are possible. One is a flat, for only for the spatial component, a flat geometry like a tabletop, for example. And you have the spherical one, which is a closed or curvature. And then you have a saddle-like structure that's an open universe kind of thing. And at the moment, the lambda CDM predictions are that the universe is almost flat. But as I mentioned, there is some kind of deviation from flatness that I said is one of those lesser contentions. So the geometry is not purely a fait accompli. We still do not know exactly what the actual geometry is like.
Thank you very much.
Thank you very much for a very deep talk and a very, very interesting talk. I have many questions, but let me ask one for now. So the equations, Einstein's equation, it looks very simple, right? Now, is it possible maybe that there is no unified theory? That, well, what do we mean by that? So you want a unified theory to be written with a single equation. So is it possible that there is no single equation that can really describe all different aspects that various other specific equations describe in suitable special cases? That there isn't a way to put everything into one equation? Is this something that can be rigorously studied, the non-existence of a unified equation?
Yeah, given that, I mean, the thing is, we have one universe and we always want to have one equation that describes it, right?
Well, that's the, I mean,
Yeah.
we make an assumption that that's
Yeah,
possible, but
yes.
what if that's not possible?
Exactly. We have to try for as long as it takes before we decide it's not possible. That's the
No,
thing.
but we can also try to prove that it's not
Yeah.
possible.
I just want to quickly show you one slide that I do not necessarily talk about in detail. It's that equation where the four forces are. There. So initially there was one unified force. It's assumed where all the four forces were unified. If you go to high enough energy, that's where your theory of everything emerges. You would think that gravity and all the other forces were the same because people have managed to actually combine the weak and strong interactions in the electroweak, no, electromagnetic and weak interaction, the electroweak. And then when you go to an even higher, the grand unified theory, you get the strong interaction also combined with the other three forces. So is there any particular reason why gravitation is part of that? It's in our nature to be curious why that's not the case. And that's why we think that if you go to higher enough energy, there must be one uh, theory that should be able to explain all the four interactions and therefore one equation that solves it all.
But but you identify the term theory with the tensor equation. Now, I don't know, you might please correct me, but when Newton was writing his laws, I don't think he was using tensor
No,
equations.
it was not.
So we had to expand what theory means equationally
Yeah.
in order to do Einstein's work. And so maybe we need such an expansion of mathematical framework. Maybe it is not possible to have one unified tensor equation, but maybe it's possible to have one unified some other kind of
Categorical theory.
more expanded. Yeah. I'm just asking
Yeah.
whether people are studying this, attempting to prove that it actually is not possible if there is any attempts in this direction.
I haven't seen, I don't know if Gödel's incomplete theory is probably one such attempt by people, but I don't think people actively work towards proving that it's not possible. It's
Okay,
not
thank
in
you.
our
Yeah.
nature to do that,
Yeah,
I think.
okay, thank
But
you.
that's a very thought-provoking question, though.
Question by Yingxia. Yingxia?
I think that's an interesting.
Yeah.
That's an interesting question. There is no reason, to me, to believe gravity will unify with the other three forces. You can say that people think that will be unified, but I would wonder why. Just because the other three forces are unified, so that gravity has to combine into at higher energy? No, there is no observable evidence for that. So for me, and gravity is very different from the other three forces because gravity is almost about geometry, where the others are not. So to me, that line, whether gravity will join the other three at the TOE, that line itself is a conjecture. And so
It
far,
is a
we don't have any, and we don't have any experimental evidence to say that will join that point at that TOD line. It's purely from aesthetic pursuit that physicists think something unified as one equation will look beautiful, which beauty always be the nature of the nature. The nature always like beauty, so that it will be drawing that line eventually at really high energy. All forces are one thing, but we have no evidence of that.
Yeah. So you see, two ways of looking at it. One tells you because the three are four, unified, the fourth one should also be unified. And the other perspective is to say, just only because the three are unified, it doesn't mean that the fourth has to be unified with the three. So that's an interesting point.
Please.
Yes, thank you for that lovely talk. I think it was very exploratory. Back to the gravity and modified theories of gravity. So obviously there are many that are existing today because we don't have the right one yet, or one that rather explains everything. So each model that we take has certain shortcomings, or you sacrifice something, in exchange for that. So do you have a preferred, or in your opinion, is it a preferred kind of theory that you think that, again, will of course differ from scientist to scientist, but that you think is has less defects, or what is it the best thing to sacrifice, or etc. etc. What's your comment on that?
Well, if I have a preferred theory, then I am already losing the scientific method. So shouldn't be anything personal. I have been working on FFR theory for the longest time, and that might be my preferred model in some sense, but it's just simply because it's a simple generalization of general relativity, which has been tested over and over and over, and has managed to pass several observational tests. And a simple generalization of that might be the way to go, rather than making a revolutionary change, paradigm change from that. introducing torsion and other things. But yeah, I do not have a personally preferred.
Can I give you my answer to your question? The sentence is simple. The fact that it's easy to construct a bewildering range of modified gravity model or alternative theory of dark energy does not mean any of this will turn out to be correct.
Absolutely correct, yes. And just for your information, so far of all the possible choices that you have, GR is still the best.
Okay, I just want to make one comment on your unifying of forces. Okay, already the GUT, the gut theories, there are many problems by now. Okay, so since well, some whatever 20, 30 years ago, people thought that there was a unification of strong and electron weak interactions. But since then, with many more precise measurements of the electroweak interaction and calculating the beta function up to 3 loops, etc., pp, it turns out that the strong and electroweak coupling constants, they don't join at a certain point. And if you look at these gut theories, for example, like SU5, then of course it gives you completely wrong the lifetime of the proton. So it's already at that point where there are many problems to talk about a unified theory, and going whatever 3 orders of magnitude higher in energy, I think it's even worse.
For that, do we have questions or comments from the online audience? Okay. I don't. Oh, can you read it, Reina? I don't have anything in front of me.
Okay, Prof. Amare, there's a comment here from Prof. Sekazim Tingwa. Okay, just to quickly tell you, he is at the U.S. Nuclear Regulatory Commission, okay, and Princeton University, and he says, good afternoon, everybody. Thank you very much for a very exceptional overview of gravity and cosmology, and he also asks that we please ensure that the slides of this presentation are posted timelessly. So I undertake to make sure that we will do that. Also, there are some other comments from people saying, thank you very much for a fantastic presentation. Thank you, Prof.
Thanks. The time to thank the speaker. So thank you very much, Amare, for a very nice talk that induced lots of questions.
Thanks.
And I'm glad to see that there are lots of young people here that might find a solution to all these problems. It won't be me, might not be you, might not be Inge, but certainly some of the young people in the audience. So thank you very much, Amare, again. And before I forget,
thanks a lot.
We want to give you a little
thank you so much.
Famous Bizarro magazine.
All right.
Yeah, so thank you very much.
Okay.
And
yeah. Okay.